Hello, this is Walker Physics 4th edition, and we're in chapter 6 and the end of the chapter questions, and we are on question number 53. A car is driven with constant speed around a circular track. Answer the following questions with yes or no. Is the car's velocity constant? Okay, just because his speed is constant doesn't mean the velocity is constant. The velocity is constant if it doesn't change. It's not changing speed, that's the magnitude of the velocity, but it is changing direction. If you remember, a vector has an attached direction to it, and if the velocity is going north, it has to continue to go north. If it moves, then it's accelerated. Okay, that's why you feel an acceleration if you go the same speed around a curve. If you're going on a straight stretch and you go around a curve, it feels like you got faster because you accelerated. You are moving your steering wheel, and so that is an accelerator, just the same as a gas pedal. So A would be what? No. Okay, its velocity is not constant, it's accelerating. What about B? Is its speed constant? Well, it said that its speed was constant, so I assume that yes, it's constant. How about C? The magnitude of its acceleration. Okay. The magnitude of its acceleration. Well, acceleration is going to equal the mass of the car times the square of the velocity of the car divided by the radius of the circle. And that doesn't change, so that's going to be constant. The direction of the acceleration constant. Okay, here's where you will make a mistake if you are not thinking clearly. What is happening? The velocity is moving, okay? I'm going this way, okay? There is a force that is pulling me this way, which means that I drop down, okay? Now I'm going this way. And there is a force, which means I drop down, and now I'm going this way. And you're going to see that your direction of acceleration is always the same. Okay, so is the direction of its acceleration constant? This really got me. It's constant in that it's pointing to the same place, but that's not constant. This acceleration is heading south. This acceleration is heading east. This one is going west. This one's going southwest. So it's pointing to the same place, but since it's at since the car is at a different location, the direction of the acceleration would have to be always changing. So that was tricky. I thought this was an easy question. That was a good one. I like it. This is question number 54. A puck is attached to a string, undergoes circular motion on an air table. If the string breaks at the point indicated in the figure, subsequent motion of the puck is best described by A, B, C, or D. Well, let me draw the picture. Okay, so I've got a puck going around in a circle. Okay, so by the time it gets to D, this is D here. By the time it gets to D, the rope snaps and it keeps going. Okay, so which direction do you think it's going to go? Is it going to continue in its curve towards A? Is it going to do a reverse curve and curve towards C? Or is it going to continue going straight, which is B? I think it will continue going straight because if let go, it has no forces on it. And if this is a frictionless table or whatever that means, it'll just continue to go in a straight line after there's no forces put on it. The only reason that it was going around in a circle was because it had a forward velocity and it had a force towards the middle, which kept changing the direction of the velocity, and it made it go in a circle. As soon as that was broken, there was no force, it went in a straight line at the end of that. Okay? All right, this is number 55. When you take your 1,300 kilogram car out for a spin, you go around a corner of a radius 59 meters with a speed of 16 meters per second. The coefficient of static friction between the car and the road is 0.88. Assuming your car doesn't skid, what is the force exerted on it by static friction? All right, so we have only learned one formula, and it's the same formula. Oh, that's cool. That's in yellow. Let me change it. F equals ma, and we're going to see that acceleration is equal v squared over r. I wrote in the last slide m v squared over r, but this is the m right here, so it's actually force equals m v squared over r, centripetal force. A centripetal acceleration, which is a sub cp, is the square of the velocity over the radius, right? So I'm going to substitute this in here, and so you're going to have force centripetal. Now, the centripetal force is what is making it go around the curve, and that is the tires. The tires, the friction force, the static friction force of the tires is what's making you go around the curve. If there was no friction at all, if it was just, ice on ice, it would slide right off the outside of the circle. It would not go around the circle. Couldn't. So what's happening is the friction force is the centripetal force. And the 0.88, I think, is a herring. I don't know anywhere to put it. I think that that's what it means if you were asked how fast could you go around that curve without skidding, then you would need to know that, because it would be something like mu of static friction times the mass, something like that, or it needs to be force, so maybe mg or something like that. So it's not being asked. So this is just F equals ma. I've got m, I've got a, because I have v and I have r, so I have everything I need. So I don't think we're going to use that at all. All right, so let's fill it in. Centripetal force is going to be equal to its mass, which is 1,300 kilograms, times the square of its velocity, so 16 squared is 256, divided by the radius of the turn, which is 59 meters. So 256 divided by 59. Okay, so your acceleration is 4.338, okay, times 1,300 gives me a centripetal force of 5640.68. All right, so once you get to thousands, I wouldn't put it in newtons. I would put it in kilonewtons. So I would put this as, looks like this is 2 significant digits, this is 2, this is 2, this is 2. So I would put it as 5.6 times 10. Kilonewtons. I was going to put it in scientific notation, I don't know why, but 5.6 kilonewtons. All right.